Let's talk about flux. I guess the days are gone in which people immediately throw out the word flux capacitor. Yes, flux capacitor is not really a thing to my knowledge, but apparently it will be in the future. So flux, more specifically, let's talk about electric flux. So imagine that I have these electric field lines going from one side of the paper to the other. And I want to have some sort of sense of how much of this electric field actually goes through a surface. So if I take some surface right here and I put it like this, I have some indication. I can draw as many arrows as I want, but I have some indication of the number of arrows that pass through this surface. If I instead take my surface right here, and let's go for that stunning visual effect. Ooh. And now I move it this way. Well, I'm not going to have any arrows going through it, even if I drew it right here. It doesn't count. We're not doing the Robin Hood splitting the arrow kind of thing. And obviously, why does Robin Hood win when he hit the exact same spot as the previous person? So anyway, we need to somehow deal with explaining the difference between these two. And so what the physicists came up with is this idea of an area vector. I say physicists, probably the math people did this first. An area vector A with a vector symbol over it. So first talk about area vector, and then we'll get back to the electric flux. So if I have this piece of paper right here, it has a certain area, but I want to be able to describe a direction for it. Now, when I've asked students this question, some of them will immediately come up with, well, that direction, or they have some sort of spinning arrow, but you need a direction to describe the direction of this area. And so what the powers that be decided was that in order to describe the direction of the surface, we need something perpendicular to it. Now in this case, it's a nice simple case where I can have up being the direction of the area vector because it's basically the same everywhere. And it's just supposed to be understood that the area vector is perpendicular to the surface. Now, if I have a curved surface, say something like this, then my area vector will be pointing that way here and that way here. And it will vary depending upon where I am on the piece of paper. But for right now, let's deal with a nice flat surface where it's perpendicular to the surface. The magnitude of the area vector is just the area of the surface. If you think about that, this piece of paper has two sides to it. I could have an area vector pointing up, or I could have an area vector pointing down. And both are perfectly fine mathematically. The only restriction they have on it that if it's a closed surface, the area vector points outward. Now, if it's an open surface, then you have two different directions. So if this is a side view of a surface, then I could have an area vector in this direction or an area vector in that direction. Pick one. Typically, you pick the area vector that is in the direction of whatever field is going through it. And we'll talk about the electric field going through it in just a moment. So these are the simple rules for the area vector. So if I have my coordinate system of I, J, and then K coming up towards us, then this is an 8.5 by 11 piece of paper. These are inches. So my area vector for this piece of paper would be 93.5 inches squared in the K direction, or negative 93.5 inches squared K. So it's in the positive K or negative K direction. We need to somehow be able to differentiate between the electric flux, the amount of electric field going through this area versus that area. And so since my area vector is perpendicular to it, so why don't I have an area vector going this way. In other words, I'm picking in the same direction as my electric field. I could pick the other direction, which is mathematically fine. Just typically you pick it in the direction it's going. Or I have an area vector pointing this way. Well, I want my flux here to be 0 because none of the electric field's going through this, and I have maximum amount here, and so what naturally falls out of that is the dot product. So when my electric field and my area vector are in the same direction, then the angle between them is 0, and I get sort of the full flux. And here, when they're perpendicular to each other, I want 0, and so we end up with the electric flux. It is a scalar as the electric field dot product with the area. If this is a calculus-based course, then it's the integral of E dot dA. And so that is the formula for electric flux.